Hey everyone, welcome. It's been a little while since we've had one of these sessions, so I'm glad to see all of you. And as you may know, today we're going to do one of the sessions in which we'll have some Q&A. In fact, we're going to start with some of the Q&A. In fact, I'm going to start with some thoughts about the recent announcement just the other day, just a couple days ago, the Nobel Prize in Physics. And then we're going to have a conversation with Harold Varmus, who I'm sure you know the name. If you don't, you should know the name. Nobel laureate 1989 in physiology or medicine, who has a deep understanding of science, a deep understanding of the politics of science, really brings a fantastic perspective on questions that really matter to the future of the world, right? The things that are pressing down upon us right now. So Harold will join us in roughly an hour, maybe a little less of that sort. So definitely stick around for that. But let me begin today's session by just making reference to the announcement that I'm sure you guys already saw about the Nobel Prize in Physics for 2020 being awarded to a real, a champion group of thinkers and researchers. Roger Penrose from Oxford, who is almost a cult figure to people like yourselves, to me too, actually, right? I mean, Penrose, when I was growing up, I even knew that name. It was just this individual who could use the power of mathematics to gain deep insight into the nature of space and time, gravity, black holes. In fact, when I was a graduate student at Oxford, and I went to Oxford to study with Roger Penrose. And it turned out that the things that Roger happened to be interested in that little window of time when I was at Oxford were things that I wasn't all that excited about. And I switched over from Roger Penrose to the particle physics group at Oxford, led by Graham Ross. And there is where I got involved in string theory and extra dimensions and things of that sort, which in the end overlaps quite tightly with the arena of research in which Roger Penrose has made his mark. But the Nobel Prize was awarded to Roger, half the prize that is, was awarded for the so-called the singularity theorem results, where he showed that the prediction of black holes, which you all know goes back to Carl Schwarzschild back in 1916, right? Schwarzschild writes the first paper having the first analytical exact solution to the Einstein field equations. Even Einstein himself did not find an exact solution to his own equations. Schwarzschild does. And as Schwarzschild does his analysis of the solution, it's the solution for a spherical mass embedded in otherwise empty space. And Schwarzschild's solution shows that if that mass is crushed down to a sufficiently small size, then the warpage in space-time will be so incredibly severe that nothing will be able to escape. And this is what we ultimately call black holes. That name actually didn't come until, a bit later on. The name black holes, as some of you may know, maybe you've heard me say it before, the name black hole was coined on 112th Street and Broadway in Manhattan, New York City. This is not a joke. This is true. That is the location of it was the location of the Goddard Institute for Space Studies. I actually worked for that institute when I was in high school, doing research on satellite imagery and how you can use satellites to understand various detailed features of the topography and erosion of sites on planet Earth. But anyway, there was a talk at the Goddard Institute for Space Studies in 1968, I think it might have been. John Wheeler is giving the talk, and an audience member responding to what Wheeler was talking about says, "Oh, the thing you're talking about, it's like a black hole in space." And Wheeler likes that name. He had a good feel for marketing in physics, and he starts to promote that name, and that's where the name black hole comes from. And Roger's work showed that Schwarzschild's solution, the black hole solution, doesn't require the highly idealized and therefore perhaps unrealizable conditions that Schwarzschild was invoking to have a black hole created. Roger showed there are a fairly general phenomenon of the general theory of relativity. Under very mild assumptions, you will get black holes as the result of certain physical circumstances. And that really made it clear that black holes were a generic endemic feature of the general theory of relativity. The others who shared their prize, Reinhold Gertz and Andrea Ghez, they were the first individuals to perfect means for observing with great precision the center of the Milky Way galaxy. And in those observations, they established that there has to be an enormously massive black hole at the center of our galaxy, a black hole weighing on the order of 4 million times the mass of the sun. How'd they do that? Well, you look at stellar orbits. I don't know if we have any visuals we could bring up. If we're able to, that would be amazing. But you have stellar orbits, and you watch these stars going around the center of the Milky Way galaxy, and they are whipped around at such incredibly high speeds, tens of millions of miles an hour. And when you look at the center and try to figure out what is it that has enough gravitational pull to whip those stars around in that manner, you find that whatever it is, it has to be incredibly massive to give rise to the gravitational pull whose influence you're witnessing in those measurements of the stellar orbits. And you realize that that incredible mass must be in a very small region, because you can measure the size within which this source of gravity resides. And so when you put those two numbers together, the huge mass and the small size, you come to the conclusion that there has to be a black hole there. Of course, we've gone even further. Today, the Event Horizon Telescope has taken a direct image using radio telescopes of the black hole at the center of M87, 55 million light years away. But the black hole I'm referring to now, that these astronomers won the Nobel Prize for, is, 50,000 light years away at the center of our galaxy. And in particular, Andrea Ghez, I was actually just talking to her the other day. I'm not trying to name drop here, but yes, I was talking to the new Nobel laureate, Andrea Ghez, just the other day about a celebration that she's going to be having for the 25th anniversary of the project that led to ultimately the Nobel Prize. When I was speaking to her, she didn't know she was about to win the Nobel Prize, or maybe she had an inkling of it. I don't know. But she's only the fourth woman to win the Nobel Prize in physics. So that is a wonderful, well-deserved achievement. And I couldn't be more excited for her and excited for all three of these great scientists for receiving this award. Okay, so that's an exciting moment in the development of physics that happened this week. With that, let me now turn to some of the questions that you have. And again, the conversation that I'll be having with Harold Varmus, we're going to probably begin that sometime near 1 o'clock. If your questions start to run out of steam, it's never happened actually, but if your questions run out of steam, maybe I'll bring Harold in to re-energize the conversation sooner. But I have a feeling that you will not have a paucity of questions. Okay, let's take a look at what we have here. Martin Topinka asks, Professor Brian, could you explain to me why a uniform soup of particles at the Big Bang has very low entropy? It's a good question. While structures have higher entropy, why does gravity act this way, and how does gravity and entropy interact with one another? So Martin, that's a good question, because when we learn about entropy as students, and I suspect that many on this video discussion have had some undergraduate experience in physics, but in a standard undergraduate course in thermodynamics or statistical mechanics, we learn about entropy, and we are told entropy is a count of the number of rearrangements of the microscopic ingredients that leave a system's macroscopic features unchanged. And we're told that in the form of equations, we're asked to look at the sum over all states that are compatible, all microstates that are compatible with the macro quantum state of a system. right? All available quantum states. I should say all available quantum states that are consistent with the macroscopic features of that system. Okay, so that's what it is. Now, when we start to look at examples, the primary examples of high entropy configurations are configurations where the particles are all uniformly dispersed. When we look at gas in a box, we learn that the high entropy configuration is when the gas is uniformly spread throughout the box. And we learn that the low entropy configuration is, say, when the gas is all clustered in one tiny little corner. And we learn the second law of thermodynamics, which tells us that the low entropy configuration of gas all clustered in the corner will typically disperse outward toward the state of higher entropy. Entropy tends to increase. So the high entropy state is the one where the particles are all uniformly dispersed through the box. Now that's curious because, as Martin is pointing out, when we talk about the Big Bang, we talk about the Big Bang having low entropy. You've probably heard me say this in previous of our gatherings. We always say that it's the low entropy, ordered configuration of the Big Bang, which allows for entropy to increase over time, which allows for other structures ultimately to arise. If the Big Bang itself was totally disordered high entropy, there'd be no potential for the universe to then evolve toward higher entropy if it already had the maximal entropy to begin with. So we believe that the Big Bang is a state of low entropy, high order. And yet, as Martin is pointing out, when we talk about the Big Bang, we talk about particles that are uniformly dispersed throughout space, or energy that's uniformly dispersed throughout space. Namely, we're talking about a low entropy configuration, but the state of that seems to resonate much more closely with the high entropy configuration that we learn about as undergraduates in physics. So what gives? What's going on here? As Martin is rightly pointing out, gravity is the essential new player. You see, when we learn about entropy as undergraduates, or if you've yet to do so, when you learn about entropy as an undergraduate, there will likely be no mention of gravity whatsoever. When we first learn about entropy, we learn about it in a context in which gravity is not a dominant player. And then that kind of makes sense, right? The gas in this room, the air in this room right now, is it affected by gravity? Sure, but not that much, right? Because the particles, the individual molecules are so light that they get buffeted to and fro by other forces, thermal forces, agitation, electromagnetic interactions, and those are just much stronger than the influence of gravity. So we typically, as a first approximation, just ignore gravity in everyday circumstances. But at the Big Bang, you can't do that. At the Big Bang, the density of matter and energy is so high that the gravity is so strong that you cannot ignore gravity. And when gravity comes into the story, the discussion of entropy becomes a little more subtle. What we learn is that because gravity is this universally attractive force, it can take what appears to be a high entropy configuration in the absence of gravity, uniformly spread out particles, and it can drive it to yet higher entropy configurations by causing some of those particles to fall together into structures like stars and planets. And in the process of crushing those particles together, gravity causes the system to heat up and therefore emit heat, light, other particles to the wider environment. And so we get a highly non-uniform, highly non-homogeneous configuration when gravity is strong enough, when there's enough matter for gravity to be the dominant force, because you get clumpy things here and then spread out particles there. And that's the dynamic that we believe allowed structure in the universe to form. You and me and stars and planets, galaxies, we are the beneficiaries of that uniform configuration in the early universe that then, through the action of gravity, clumped up into stars and planets, and on certain of those planets, smaller clumps formed, and some of those clumps grew limbs, and some of those clumps with limbs and brains began to walk around, think about things, and come up with the explanation that I just gave you. So that's the basic answer to Martin's question about entropy and gravity. Okay, going back to the chat here. If you have a question, just put it in the chat. Abhay Kumar, please explain singularities. Abhay, I wish I could explain singularities. I can explain some singularities, and I can explain the general idea of what a singularity is. But there are many singularities that we have yet to fully understand. And one of the most pivotal is the one at the center of a black hole, the very topic that was the focus of work that won the Nobel Prize. So anyway, what is a singularity? A singularity is a euphemism. It's a euphemism for we don't know what the heck is going on. That's all that it is, right? Now, more specifically, we typically talk about singularities in the general theory of relativity, although not exclusively. And in the general theory of relativity, there are certain mathematical solutions to Einstein's equations where the curvature of space-time blows up. It soars toward infinity. It's a curvature that approaches 1 divided by a number that itself approaches 0. So the curvature approaches 1 divided by 0, which of course is infinite. Put 1 divided by 0 in a calculator, it says error or infinity or something like that. So that's what a singularity is. Now, why do we call them out? We call them out because they're meaningless. They're mathematically meaningless. Infinity is not just a big number. Infinity is a number that in certain contexts we understand. When we talk about the natural numbers going up to infinity, yeah, we sort of understand that. Well, when we talk about the real numbers going to infinity, yeah, we pretty much have that under control. But when we talk about a curvature of a space going to infinity, that's like having infinitely curved part of space, a kink in it, or a location where it no longer looks like a smooth environment, which is what general relativity requires for physics to make sense. So a singularity in the general theory of relativity is a diagnostic. It's a mathematical tool that assures us that something deep is wrong. So what we try to do is cure singularities. We try to make sense of them. And for instance, some of the work that I've done, some of the most fun work that I've done was going beyond the general theory of relativity into string theory that combines general relativity and quantum mechanics. And in that setting, we found that certain singularities that Einstein's theory could not cope with, the math of string theory could cope with. In other words, the infinity of general relativity was tamed into a finite value, a finite number. And that is generally what we view as a success story, where a new theory goes beyond a previous theory and allows you to address things that the previous theory was impotent to address, couldn't address at all. But when it comes to more exotic singularities than the ones that we have been so far able to handle, like the singularity at the center of a black hole or the singularity at the Big Bang, nobody has really convincingly figured out how to resolve those singularities. And so those are open questions. What truly happens at the center of a black hole? What truly happened at the moment of the Big Bang? We'd like to get to a point where we don't just shrug. And that's the goal of a lot of the cutting edge research that's going on today. All right, what do we have here? Why does time only move in one direction? Somebody asked that question, but it scrolled by too quickly. So I don't know who asked that question. So sorry about that. I should keep my fingers off the chat. Every time I touch it, it scrolls too fast. All right, I'll answer the question. Why does time only go in one direction? Again, we only have partial answers. Entropy, which Martin asked about earlier, is part of that answer. We believe that although the laws of physics are agnostic about past and future, they treat past and future in exactly the same way, completely symmetrically, even though the equations don't care about what we humans call past and future. entropy, this measure of disorder, does have a bias. It does increase toward the future. So if you anchor entropy at the beginning of time, call that the Big Bang, if it's anchored at a low value, then entropy will typically have a graph that just goes upward. Now and then it can come down. It's not an ironclad law, the second law of thermodynamics. It's a tendency. But that tendency is so overwhelming that indeed entropy toward the future goes up. And so that's part of the answer. But is it a full answer? I don't consider it a full answer. For instance, I can't answer the question, why was entropy low at the Big Bang? Now, some would say maybe that's not even a question worth thinking about. It's just an environmental detail, an environmental quality of the universe, and you just accept it. For whatever reason, it just happens to be that that's how the universe began. But we physicists, we don't like answers like that. We're not satisfied by answers that are just so stories. We want to find deep fundamental principles. And many people have worked on the question of why the early universe had low entropy. I wrote a paper a couple of years ago that I thought was kind of fun. In the end, I don't think it actually works. But it goes back, sorry to keep referring back to you, Martin, but your question has proved to be pivotal in a lot of what I'm talking about right here. But in Martin's question, we were led to talk about gravity and entropy and noted that when gravity is part of the story, entropy has different qualities. So imagine that in the very early universe, there was no gravity. And so the uniformly distributed particles would have been the natural state of being. It would have been the state of high entropy in the absence of gravity. And then imagine that somehow a switch is flipped, not a flip is switched. A switch is flipped. A switch is flipped and gravity turns on. And then when gravity turns on, my answer to Martin's question comes into play. Things start to clump together and you reach a yet higher entropy, disordered, non-homogeneous state of being. And that could be an answer. It turns out that in the flipping of the switch, there are entropic considerations too that you need to think about that wind up suggesting strongly that the resolution that I just described is really assuming the answer. I don't know if there's some version of that story that could work, but suffice to say, people still think deeply about this question, and I don't know the answer to it. Okay. Let's see. Yeah, back to a black hole, since that seems to be a good topic for this Nobel Prize announcement week. So Kushal asks, what is inside a black hole? What is it actually? And I love the questions that are coming today. They also make me feel a little less than sage-like, because many of these questions I cannot give you the full answer to, but I can at least give you the state of play, the state of the art. So in Einstein's general theory of relativity, the inside of a black hole, nothing particularly special. So by inside, I assume you mean inside the so-called event horizon of a black hole. Now, in Einstein's theory, the event horizon is not some unusual place in the sense of there's something measurably different about being at the event horizon. You and I could just now have crossed over the event horizon of a really large black hole, and we would not have known it. That could be what's going on. We could right now be heading toward doom, heading toward the center of that black hole where we will be crushed out of existence, and we would not have known that we crossed over the edge of that black hole. There's no signpost in space that says, warning, event horizon beyond this point. It doesn't work that way. The event horizon is an absolutely ordinary, prosaic location in space from the perspective of someone who is passing by that location. And that hints at the answer to your question, because if the event horizon isn't some special sign-posted location, then when you cross over the event horizon, the space that you encounter will pretty much be like the space that you were just passing through. So the inside of a black hole, inside the event horizon, looks pretty much like the outside of an event horizon. It's just empty space. And you only really notice something unusual happening when you get closer and closer and closer to the center of the black hole, where the tidal forces, that is, the strength of gravity on your feet, if you're falling feet first, versus the strength of gravity on your head, will be much stronger on your feet than on your head. So your body will be under tension, tidal force tension. Your feet will be pulled downward toward the center of the black hole with a greater force than your head, which is a little further away from the center. And you will be what we call spaghettified. Spaghettified. That's a technical term of art, which says that you will be stretched more and more to look like a piece of spaghetti. And ultimately, you will be pulled apart into your constituent particles. But in this classical description, the inside of the black hole, other than the uncomfortable nature of being near the center, other than that, it'll look like space pretty much anywhere else. Now, when we have tried to put quantum mechanics in this story, that classical description has undergone various proposed revisions, and we're not sure which proposed revision is necessarily right, or if any of them. My friend Samir Mather, wonderful physicist at Ohio State University, we were postdocs together in the early days, back at Harvard in the 1980s or something, and he has proposed that black holes are actually big entangled balls of string. And that's a very different picture of a black hole. He's saying that we have long been confused by the pure classical Einstein description of black holes. And he says that there may not even be an event horizon. He thinks a black hole is sort of more like a star. It's got stuff in it like a star, and the stuff is this big entangled ball of strings. So he calls these fuzzballs. So Samir suggests that black holes should be replaced by fuzzy things called fuzzballs. Others have suggested that the event horizon of a black hole may be a location of extreme temperature. This is called the firewall picture that emerged from a paper whose authors are usually referred to with the acronym AMPS. The P in there is Joe Polchinski, who tragically passed away not that long ago, which is an enormous blow to physics, enormous blow to everybody who cared deeply about him. But in that paper, Joe and his collaborators realized that there's a tension between quantum entanglement and black hole physics. And one resolution to that tension they found is to imagine that the event horizon of a black hole is a real place that has a high temperature, so that anything that gets too close to the black hole is incinerated by that heat. And indeed, there may not be any space on the other side of the firewall. The firewall could be the end of space in that region. And then the answer to the question that was asked would be, what's inside a black hole? What's it like? The answer would be, there isn't an inside to a black hole. And that would be another possible answer. So this is a completely open question and a fruitful area of research, and one that maybe some of the younger members of the discussion we're having will one day have impact on that kind of question. Okay. Moreno Sanguanini asks, will primordial black holes ever be detected? And I got to tell you guys, thank you for asking all these black hole questions. It feels so relevant to this week. But again, feel free to ask anything you want, but it's kind of nice. So will primordial black holes ever be detected? So first off, what is a primordial black hole? A primordial black hole is a black hole that would have formed right around the Big Bang. So often when we think about black holes, stellar mass black holes, a black hole with a mass of whatever, 10 times the mass of the sun, we imagine that there's a star, maybe it's a red giant star, and we envision that at some point it uses up its nuclear fuel. That's important because it's the nuclear burning in the core of a red giant that creates the outward flowing pressure that supports the star against implosion, against its incredible heft, its incredible weight. When the star uses up its nuclear fuel, that outward pushing pressure goes away and the star implodes in on itself. It gets hotter and more dense at the core, ultimately setting off an explosion that ripples through the star, blows off the surface, supernova explosion. And what remains is a dense core that has no capacity to support its own weight at all. So it collapses in on itself and creates a black hole. So that's the procedure by which we believe that many black holes in the universe form. Primordial black holes would not form in that manner because there weren't any stars, there weren't any supernova, there weren't those kind of clumps of matter at that point. Instead, the idea is that clumps of matter could just immediately come together and collapse directly into a black hole. And these primordial black holes, the thought is, might still exist. Now, here's the issue. Black holes evaporate when you take quantum mechanics into account. So this is something that Stephen Hawking taught us in 1974, that even though black holes are completely black, according to Einstein's vision, Einstein's equations. I should say Einstein's equation, because Einstein didn't actually believe that black holes would be real, but that's a separate story. But Einstein's math says that nothing gets out of a black hole. But Stephen Hawking showed that when you include quantum physics, which Einstein's math does not include, stuff can get out of a black hole. So if a black hole is sufficiently small, then as it radiates, it'll just evaporate all its heft. We don't know exactly what would be left at the end, but we suspect that the black hole itself would be gone. So if all primordial black holes have evaporated, finally to the question that was asked by Moreno Sanguinini, I like to say that name, then if they've all evaporated, they won't be around to be detected. If any have persisted, and there are ways that they might have persisted, then yeah, in principle, one day we might detect a primordial black hole, which would be enormously exciting, enormously exciting. Okay, Session asked, please ask the questions one by one. I can't do that because they're scrolling by. Maybe there's a way in which I could. You're right, it would be nicer, I guess, to have first come, first served on the questions, but we'll have to figure out a way of doing that. I can't do that easily right now. Let's see, so M5 says, I just expected in the first step you would interview one of the Nobel laureates in physics, Professor Ghez, Professor Penrose. Oh, come on, M5. There is ample opportunity for us to have conversations with all sorts of thinkers. And at some point, we will have the newly minted Nobel laureates in physics. But if, as Harold no doubt will tell us in the next part of our discussion, once the announcement is made, life as a new Nobel laureate is incredibly hectic. So I'd rather have a conversation with them when things settle down just a little bit. Okay, what else do we got here? Upgrade says, if nothing can move faster than light, how does anything go into a black hole? Upgrade, I'm not exactly sure I understand the question, because if something goes into a black hole, it can fall in at whatever speed it likes. It doesn't have to go faster than the speed of light. So it's more the reverse story. In fact, let me tell you that there's an interesting analogy that I sometimes tell my students when I'm teaching about black hole physics, which is you can liken falling over the edge of a black hole to falling over the edge of a waterfall. What do I mean by that? Well, imagine you're in a boat, right? And there's a big waterfall right over there. And you're like, well, I really don't want to fall over that waterfall. What do is you turn your boat and you start to paddle upstream. And you hope that you can paddle faster than the water is flowing. Because if you can't paddle faster than the water is flowing, you're doomed, right? You're going to be dragged to the edge. You're going to fall over the waterfall. Now, what's the analogy with black holes? There is a real sense. This is not cartoon physics. This is a real sense in which you can describe a black hole, the edge of a black hole, as a region where space itself is falling over the edge. Space itself is flowing over the edge of the black hole. And indeed, at the edge, the speed of space is equal to the speed of light. Think about that. Why is that important? Well, if you happen to find yourself at the edge of a black hole and you don't want to fall in, you're kind of in trouble, right? Because you can't go faster than the speed of light. Nothing can, no material object can. So if space itself is flowing at a speed equal to the speed of light, you are doomed. And that's why you are doomed if you get right to the edge of a black hole. If you're outside the edge, then the speed of space is less than the speed of light, and therefore, in principle, you can get away. In principle, you can turn on your rocket engines and paddle upstream, as the person in the boat would do with the waterfall. But once you get to the edge of the black hole, can't go faster than the speed of light. Space itself is flowing over the edge at a speed equal to the speed of light, and that is one way of thinking about why you cannot get away. Why you cannot get away. Okay, all right, a couple more before we turn to the main event, for which I am the warm-up here today. Vinod asks, is there anything faster than light? And the answer to that question, Vinod, is yes, in a sense. So you should bear in mind that even in Einstein's special theory of relativity, the precursor to the general theory of relativity that Einstein wrote down in 1905, in that theory, the only prescription is that no material object can go through space at a speed greater than the speed of light. And it's important to hear the first half of that sentence, because just to give you an example, when I say that nothing can go through space at a speed faster than the speed of light, that, for instance, does not restrict the speed of spatial expansion to be less than the speed of light. So if you have two galaxies in space, right, and if space itself is swelling and thereby dragging the galaxies apart like poppy seeds in a muffin that's expanding, the poppy seeds are dragged apart. Similarly, if the galaxies are being dragged apart by the swelling of space, there is nothing that says that the speed of recession of those galaxies needs to be less than the speed of light. The galaxies are not moving through space. The galaxies, in a sense, are stitched into the fabric of space, and they're only moving because the fabric of space itself is swelling. And there's nothing in Einstein's declaration that restricts the speed of spatial swelling, the speed of spatial expansion. And we do believe that, and our cosmological mathematical theories support this, that objects can move apart faster than the speed of light because of the expansion of space. So the answer to your question, Vinod, is yes, in that sense. Raghav asks, why does string theory stop with 10 dimensions? Why not more or less than 10? And first off, I should say that, just to be clear, the most modern incarnation of string theory, often given the name M theory, involves 10 dimensions of space and 1 of time. So 11 does come into the story. So right there, it's bigger than 10 if you were referring to space-time. But there are what are known as non-critical string theories, in which it's a little subtle, but in a time-dependent scenario where a certain field called the dilaton field, if it changes in time in a particular way, then the math does allow the number of dimensions to differ from the critical value that you make reference to. So there are versions of string theory that I think fit well into an affirmative version of your question as opposed to the negative version, that in those contexts, you can have different numbers of dimensions. Nervisa says, I'm taking my lunchtime to listen to this. Is that crazy? I'll let others weigh in on the state of sanity of somebody who would waste their lunch thinking about space, time, matter, black holes, energy, the universe. Why would anybody want to spend their precious time thinking about things of that sort? Well, as well you can guess from someone who has spent a lifetime thinking about these things, there is a reason for doing so. And I think everybody who's here understands those reasons quite well. So enjoy your lunch, stay with us, and hopefully your lunch break lasts long enough that you can stay with us for the conversation that I'll have with Howard Varmus starting in about 10 or so minutes. Okay. Vivek asks, what about warp drive? And, you know, there is, look, anyone who's watched Star Trek, you know, at least in the original version, James T. Kirk talking about warp factor 5, which, if I remember the conceit of the script writers, warp 5 meant 5 cubed times the speed of light. And the rough idea, if one tries to make sense of this, is that if the speed of light truly is the speed limit to go from here to here, if you were to go in this direction, you're never going to go there faster than the speed of light. But if you're able to bend the fabric of space, taking that destination and bringing it effectively closer to your origin so that the new journey that you take is different, shorter, then you're going to get to that destination quicker than the speed of light. And therefore, effectively, you would have traveled faster than the speed of light, even though there would never be a moment when your actual speed would exceed that of light. And that's sort of the vague idea that I think the script writers had in mind. Scientifically, there have been people who have written down mathematical versions of warp drive. I can never, I should look it up because now I'm embarrassed, but there's a, interesting physics paper by a physicist, Alcubierre. I hope I'm not saying his name incorrectly. Someone can correct me in the chat. Who put some mathematics behind the idea of a warp drive and now has a warp drive named after him. Whether you can ever realize this general relativity version of warp drive in the real world is certainly an open question, but it is at least interesting that similar ideas to the ones that were introduced in a completely fantasy world, science fiction world of Star Trek is something that in the physics world people have thought about. So yes, Bayarki has written down the spelling of Alcubierre, but I don't know if I'm pronouncing it correctly. So what I really need is someone to give me the phonetics. I know how it's spelled. I just need the phonetics. Mark asks me did I read the book that I sent to your secretary in the US called Path to Life? I've not read it, Mark. I'm sorry. I didn't even know that it came in, and that should not be taken personally. A lot of things come in that I just don't have time to look at everything. But now that you mention it, I will remember to ask her, and we'll take a look. So maybe by next time I will have had a chance to take a look. What do we got here? 12:46. Let's just do a few more minutes before we move on to the main event. Shavuk asks, how many dimensions can a black hole have? And that's a good question, because when Schwarzschild wrote down the black hole solution that I mentioned back in 1916, he was imagining 3 dimensions of space and 1 of time. And, for the most part, that's where a lot of the research on black holes has taken place. But with theories of extra dimensions like Kaluza-Klein theory and string theory and various supersymmetric particle physics theories, people have written down black hole solutions in a whole host of different dimensions. So black holes are not restricted to 3 dimensions. In fact, in higher dimensions, people have studied all sorts of black objects that are called black brains, BRANES. And black brains are objects who have various numbers of extended dimensions, but have the property that if you get too close, you can't pull away. So black holes are a very general phenomenon. They're not limited to 3 dimensions of space, and they're not limited to the form that we usually have in mind, the spherical event horizon around a singularity, at the center. That is a good image to have in mind, but it's not the only image for the form that black holes can take. Paul, what is the heat death of the universe? So the heat death of the universe is a distant time when, going back to Martin's question at the beginning, where we imagine that the low entropy starting point of the universe, entropy has grown and grown and grown over time. Some orderly structures have formed because of gravity, as I mentioned, crushing particles together. But in the far future, we do imagine that ultimately entropy wins out completely and everything disintegrates into a bath of particles that just waft through an ever larger and ever colder universe. So it's kind of weird. We call it the heat death because we're talking about entropy and thermodynamics, but we aren't imagining that it's very hot. The heat death is very cold. The heat death is when everything has just thermalized, in the sense that everything comes to pretty much the same very low temperature uniformly throughout space. And then the idea is not much happens from that point forward. It's not that nothing can happen, and that's an interesting footnote to that answer. And again, I'm not, as you know from these previous sessions, I'm not into advertising things here. But if you are interested in the heat death and the various possible fates that life and mind and the universe might have, check out my book. Get it from the library. You don't have to pay for it. Find a bootleg PDF copy online. They do exist, unfortunately, but they do exist. And you can read, especially chapters 9, 10, and 11. Really turn from today and take you right into the future, with the heat death being one of the possible fates that our universe faces. All right. Does friction exist in space, Shanti asks. And yeah, it does. Not exactly in the form that you have in mind. I mean, sure, there are, I say a planet moves through space, yeah, it can brush up against the microwave background radiation. In principle, there's a little bit of friction there. But the friction that I have in mind is of a different sort. It's a friction which answers the following question. You all have gone to the Science Museum. When you've done that little demonstration, you take a quarter or a nickel or something, you put it into a funnel-shaped trajectory, and it rolls around, and real fast, and it goes right down through the funnel. And that demonstration has led many to ask me about, look, in the general theory of relativity, the sun kind of warps the space like the funnel in the Science Museum. And we always picture the planets as sort of rolling around this funnel-like shape. Why don't the planets, like a quarter, or if some of you from out of the country, a coin, why don't the planets, like coins, spiral into the center? And the answer is planets do spiral into the center. Why do they do that? Well, the coin does it because of friction. That's what the relevance to Shanti's question is. You know there's friction with the coin. You hear it, right? You hear the coin rolling. So energy being dissipated from the coin into sound waves, among other things as well. When planets are in orbit around, say, the sun, they jostle the fabric of space and send out gravitational waves, gravitational radiation, not sound radiation, but gravitational radiation. And that carries away energy, just like the sound waves carry away energy from the coin. And so if you wait long enough, a planet like the Earth will spiral into its star if it isn't destroyed before that by some other process. And for the sun, you can calculate how long it will take the Earth to spiral in. And the answer is about 10 to the 23 years. So, you know, it's a long time. Right now, we're only 10 to the 10 years since the Big Bang. And we're talking about 10 to the, say, 20 years before the Earth will spiral into the sun like a coin into the funnel. But in principle, it will do that. And therefore, you can think of that as a kind of friction in space. Woody tells me to turn on Super Chat. I don't know what Super Chat is. Is there a thing called Super Chat? There's a thing called Live Chat. Maybe that's what I should have had on. I had Top Chat on. I never really know the difference between those two, but I've now taken your suggestion, Woody, and I've got Live Chat on for whatever it is worth. Akash says, what do you think about Zeno's paradox? And asks that question with more question marks than anyone has previously used. And therefore, you win the award, Akash Kumar, for the greatest number of question marks. What do I think about Zeno's paradox? It's a nice paradox. How do you solve this paradox? Well, it's not that hard to solve this paradox. You see, Zeno is saying that motion should be impossible, right? Because for my hand to go from here to the camera, it has to go halfway, and then it has to go half of the remaining distance and half of that and so forth. And it seems like there are an infinite number of steps, and therefore I will never be able to make it. But of course, the error in Zeno's reasoning is to not take into account that the smaller the step, the less time it requires for me to take that step. And indeed, if you take into account that as the distance goes, the remaining distance goes to zero, the remaining time to cover that distance goes to zero, and use a little logic or a little calculus, you realize that, of course, we can cover a finite distance in a finite time. So the error is the implicit assumption that every single step will take an amount of time such that when you add up all of the increments, it will be infinite. No, an infinite number of numbers need not add up to an infinite value. You all know that, right? A half plus a quarter plus an eighth plus a 16 plus a 30, it all adds up to 1. It doesn't add up to infinity. And therefore, even though there are an infinite number of steps, because each step takes an infinitesimal duration of time, when you add up all those infinitesimals, you can get a finite answer, and motion is possible. So that is the end of Zeno's paradox. Okay, so with that, let me just take a drink of water here. All right, one more. Now everyone's using a lot of question marks. Perhaps I shouldn't have said that. Vince, and now I'm sort of rewarding question marks. A little bit foolish of me. Why haven't we found the graviton? What would change if we could prove that it exists? Vince asks. And first of all, what is the graviton? For those of you who may not be familiar with the term, the graviton is meant to be the smallest packet of gravity, the messenger, so to speak, of the gravitational force. The photon is the smallest packet of the electromagnetic force. The photon is the messenger of the electromagnetic force. And so the graviton is to gravity what the photon is to electromagnetism. Why have we never found the graviton? We have found the photon. Completely understandable. Gravity is fantastically weak, so much weaker than the electromagnetic force. I love demonstrating this fact experimentally. It's the only experiment that I, as a theorist, have complete confidence that I can carry out. Here's the experiment. Are you watching? Please watch. That's it. I just proved that the electromagnetic force is much more powerful than the gravitational force. Why? All of Earth's gravity is pulling on this piece of orange rubber here, okay? All of Earth's gravity. Earth is big. My little puny muscle over here, I'm not a strong guy. My little puny muscle just beat out the entire pull of Earth's gravity. My muscle is using nothing but the electromagnetic force. And the reason my muscle can do that is because the electromagnetic force is much more powerful than the gravitational force. It's, depending on how you measure these things, but it's roughly a billion times stronger than the gravitational force. So if you're looking for the smallest packet, the graviton, the smallest packet of the weakest force, man, that's a challenge. That's an incredible challenge to find the smallest packet of the weakest force. So am I surprised that we haven't found the graviton? No. In fact, there's some who suggest that maybe there's a sense in which we will never literally find a graviton, and yet it might still exist. It might just be always so washed out by other influences in the world. I don't think I think we'll probably one day, where one day might mean 10,000 years from now, have experimental evidence for the graviton in the way that we have experimental evidence for the photon. But that's the answer. Vince, to why we have never found the graviton. All right, guys. So thanks for all of those questions, and you can continue to ask them as we now turn to the next part of the discussion here. And, this is a little bit of a different discussion than some of the previous ones that we've had, but in many ways, it's the most important discussion that we've ever had in this series of your daily equation or World Science U interviews, or whatever you want to call it, because this is a discussion that, doesn't just tickle the mind. This is the one that is relevant to our very existence. So I'd like to now introduce Dr. Harold Varmus, who's currently a professor at Weill Cornell Medicine. He won the Nobel Prize in 1989 for his work in cancer research and is head of the National Institutes of Health, the National Cancer Institute, and the Memorial Sloan Kettering Cancer Center in New York City. Prior to his nomination to the NIH, Dr. Varmus had been a member of the UCSF faculty for over 20 years and received degrees in English literature, we'll talk about that, and medicine from Amherst College, Harvard University, and Columbia University. He has long been a voice at the intersection of politics and science. And with that, I'd like to welcome Harold to our discussion. Hey, Harold, how are you doing?
How are you, Brian? Thank you very much for having me.
I'm very good, thank you. Where are you?
Well, usually I'm up in Columbia County, New York, not too far from your place in Cairo. Right now I'm in my apartment in New York, but heading up north as soon as we're done.
Yeah, I mean, how we've been in New York now and then. Sometimes it's uncomfortable as I'm dodging people in the street who aren't wearing masks. Most are.
Most people are wearing masks up here, and it seems it's opening back up. We're dining out. We're going to museums that are much less crowded than usual. It's actually quite a pleasure to be up against your favorite pieces of art without 1,000 people crowded around you, whether they're infected or not.
Right, the silver lining of it all. So when you've eaten out, have you eaten indoors or only outdoors?
Only outdoors so far.
Yeah.
The weather's been nice, and it's very pleasant to be outside for the most part.
Yeah. So I'd like to turn to the pandemic in just a moment. But before we get there, I thought it'd be, well, I would find it interesting if you're willing to spend a little bit of time talking about your own background, which is,
of course,
rich and unusual in a wonderful way. So as I mentioned in the introduction just a moment ago, you majored in English in college.
Mm-hmm.
Many people who go on to have illustrious careers in science, to win the Nobel Prize in science, were kids like me who did science fairs, the math team, all that sort of stuff. Yeah. So that wasn't your upbringing, right?
It wasn't. I grew up with a father who practiced family medicine, and I thought I was destined to be a doctor someday, but I was interested in reading and politics and other things, sports. And I went off to college and found myself even more diversified, interested in philosophy, briefly in physics until I found out how hard it really was. And then I went off to graduate school in literature after writing a thesis about the novels of Charles Dickens. And while I was at graduate school, I had an epiphany, thinking that if I went into medicine and didn't turn up for an appointment, patients would be actually disappointed. If I was a teacher and didn't turn up for class, students might be happy to go home. And I also felt that the part of my brain that did have some aptitude for science was atrophying, whereas I thought I could manage to continue to be a thoughtful reader and an engaged reader at a time when I was doing science or medicine. Yeah. So I went off to medical school at an interesting time when molecular biology really hadn't yet begun to permeate the thinking about disease. But I was seeing clues that we were going to understand genes and begin to understand disease at a much more fundamental level. I got exposed to some people who were doing such work and studying at Columbia College of Physicians and Surgeons, where I began to see that we were going to learn that a disease like sickle cell anemia was going to be understood as a mutation that the result of mutations that affect very few genes, and yielding prospects for thinking about diagnosis and prevention and therapy in ways that were really unprecedented.
Yeah.
And I chose the right area to get into to work on this problem, namely cancer, which is a disease of the genome, and where molecular biology has had huge effects already.
So I want to talk about that in a minute, but there's one thing I read that you wrote that it was actually in an interview, I believe, in a 2012 Journal of Clinical Investigation.
Mm-hmm.
And if you don't mind, I just want to read it because it's a really wonderful and unusual way of getting into a scientific frame of mind. You, in speaking about Columbia Medical School, you said, "I went there thinking that somebody who liked words and books was interested in the workings of the mind would be a psychiatrist, but then I became interested in internal medicine because of its narrative aspects." Can you flesh that out when you?
Sure. Yeah. Well, first of all, I still think that somebody who has more patience with ill individuals would be attracted to psychiatry with under some circumstances. But when I first found myself in a room alone with a patient who undoubtedly had an interesting story, but whose mind was too chaotic to be able to relate it, I realized that I really wasn't built for that kind of thing. But when you went to talk to a patient who had a disorder of the heart, the lungs, the kidneys, they were able to tell a narrative that allowed the astute physician, which I wasn't necessarily at that point, to try to unravel a story and make sense of it and think about the relationship of the patient's experience to the physiology of disease. And then I think at a later level, even though I never ended up practicing medicine, the ability to relate that story to something that was happening at a molecular and genetic level in that individual gave rise to new ideas about how one might do a better job in trying to repair the defects or coming up with public health measures that would reduce the incidence of disease.
Yeah. So 1989, you win the Nobel Prize for the insights that you were briefly referring to, insights into cancer, its relationship to viruses. We had a conversation just a couple of weeks ago with Adam Rees, another Nobel laureate in physics. Mm-hmm. And one thing I asked Adam was, I said, look, you won the Nobel Prize. At that point, you've kind of reached the pinnacle in some sense of your field. Did you think about doing something else at that point? And Adam was like, no, it's like I do I do astronomy. That's the only thing. For you, though, am I wrong in saying that winning the Nobel Prize was a turning point of a sort? Is that accurate?
I think it is accurate, not because of some change internal to me, but because of the world's perception of me. Up until then, I was successful. I can't deny that, but I was a scientist. People who were interested in the molecular biology of cancer were interested in what I did, but I wasn't in any sense a public figure. But the prize did change the way the world viewed me and the way the government viewed me. I was called upon, in part because I was a Nobel laureate and because I had had some experience with the NIH, to begin to advise the NIH about how it was organizing policy and helping to support career development and other things. And once I got engaged in that process, not only did I find it interesting once I was presented with the opportunity to help craft policy, but people who were working with me decided that maybe I would be a good person to help lead the organization. And then when that offer came at quite a high level, asking from the president to be offered the directorship of the NIH, frankly, I jumped at it. I was in a good position because Donna Shalala, my boss at the Department of Health and Human Services, and Clinton himself were amenable to the idea that I could continue my research career at some lower pace, so I didn't have to give up research, which many people do at that stage. So I've actually maintained a laboratory to this day as I enter my 80s.
Wow.
So I do laboratory work, not with my own hands, but with through the hands of postdocs and students and technicians. But I'm engaged in research, and despite the litany of leadership positions that I've held over the last 30 years or so, I've been able to keep an active interest in science, for which I'm quite grateful.
Right. Now, let me, if you don't mind, I would like to turn to the elephant in the room, if you will, the pandemic.
Sure. Yeah.
And I just want to say, back, it must have been 20 years ago, I was at a talk at the New York Academy of Sciences, and there was Laurie Garrett, I believe is the journalist's name,
yes,
was talking about the possibility of tragedy hitting us with some sort of viral pandemic. And I left that lecture kind of terrorized. And of course, an hour, 2, 3, I thought about it, and then it dissipated away and I stopped thinking about it, right? And then there was a World Science Festival program where you, and I believe Laurie was also in that program, maybe others in it as well. And again, it came back to mind, this possibility and so the point I'm making is you and others knew this was potentially coming. And yet it's happened now, and it's clear that we really weren't prepared. So is it that we weren't prepared, or were we prepared and we botched the response? What's your view, from 30,000 feet, of why we find ourselves in this predicament?
Yeah, well, your description of your own reaction is actually emblematic of the way society responds to pandemics, especially at a time when we think science is very powerful and we're not really threatened by the kinds of plagues and outbreaks that have been recorded during history, from the time of the 14th century plagues in Italy to the influenza epidemic of 1918. And indeed, there is a story to be told here about what happened after the influenza epidemic of 2008 and 9. At that time, I was a member of Obama's Council on Scientific Advisors, Science and Technology Advisors, and we wrote a couple of fairly stern reports about how the nation not only needs to up its game to deal with the influenza epidemics of that period, the first year or so of the Obama administration, but also to prepare for the next ones. And one of the things that has happened during the current pandemic is that about half of the old Obama PCAST, as we call that group, got together, and we've been talking about what we should be doing during COVID-19, and how we try to prepare the country and the world for what will inevitably be the next one. In between the flu epidemic of 2008 and 9 and current time, we've had a number of other significant outbreaks. They haven't endangered all of the world at the same level, SARS and MERS and Ebola and Zika. But it tells you that because people travel rapidly, because the interaction of humans and animals is still a very intimate one, and because viruses in particular do have the ability to spill over from infected animals into human populations and spread, we're going to have more epidemics, and there's no doubt about it. And the question is whether this one, with this tremendous severity and the incredible attention that everyone's given to it, will actually sustain an interest in doing the things we know we should do and could do to be better prepared. We were somewhat prepared for this, but mostly the disaster is just the consequence of botched oversight.
Right. So, I mean, you have been quite forthright and critical about certain aspects of the response. I just want to read from your own New York Times op-ed, a particularly telling description. You wrote that the CDC, the federal agency that should be crushing the pandemic, is promoting policies that prolong it. That means that local, state, and organizational leaders will have to do what the federal government won't. Now, that's pretty, I mean, from someone who's been in the positions that you have held, that is a pretty telling description of what's going on. So what's the source of this? I mean, those of us on the outside conjecture what's going on here, but what's your view? How could an organization that was the premier disease-focused organization on the world stage have gotten to a place where someone in your position is basically telling people, ignore them, they're doing the wrong thing? How could that?
Well, it's painful to say that, because the CDC indeed is, one of the world's, if not the most prestigious organization, one of the most, and it's painful to say that it's advising the wrong thing. To happily, our op-ed and many other statements by other public health engaged people led to a reversal of that policy. But what they were saying was basically, we don't need to test asymptomatic people, which is, idiotic in this context where we have a pandemic caused by a virus that becomes highly transmissible before it produces symptoms. So people don't know they're sick, and we're seeing this on a big stage in the last couple of weeks, when people who are in the news anyway every day are being paraded before the public as people who say they have no symptoms, they're fine, but of course they're producing virus and they're at risk of transmitting that virus, especially if they don't wear a mask, don't respect social distancing, and I don't know how often they wash their hands, but the fact is that the virus is being transmitted in a terrible way. When we know what to do, obviously, if we had a vaccine to put into effect, if we had drugs that really protected people against viral infection, I think this is a place. Actually, there is a teachable moment here that goes well beyond thinking about this coronavirus, and that is related to the Nobel Prize that was announced on Monday to three investigators who played an important role in discovering the cause of we call hepatitis C infection, and allowing for the development of diagnostics in the late 1980s and a few years ago, therapeutics to prevent death from hepatitis C. People often don't realize that we knew about viral infections for 100 years before there were reasonable therapies, and now molecular biology and new kinds of drug development have allowed the development of drugs like the hepatitis C drug, drugs against HIV, that do an unprecedented thing. They allow us to combat a viral infection. And I'd like to see that happen in the case of COVID-19 as well.
Now, Tony Fauci, as I understand it, is a friend of yours.
Indeed, one of my closest friends.
So I in no way am asking you to be critical, but I do have a following question, if you're willing to address it.
Sure.
Especially early on, were there any moments when the response that he was giving when the administration was saying nutty things, did you ever in your living room watching him on TV say, come on, Tony, really push back. We got to push back harder. Did that ever?
Well, I guess I respect Tony too much to say that I was being critical, but I was aware that he was under a lot of tension, and my assumption was that he was saying what he thought was reasonable to say in the inner sanctum, without publicly antagonizing the people he needed to reach if he was going to make any headway. And I think he's been a pretty good purveyor of what needs to be said to the public. In the very beginning of this pandemic, we didn't know a whole lot about this virus. We didn't know exactly how it was being spread. There was concern, for example, about how we should best deploy the masks that we had. There was no doubt that the stockpile was somewhat depleted of some of the most important personal protective equipment that we needed to keep our healthcare workers maximally safe. So there was a period in which really had to be established that this virus was being transmitted largely by the aerosol route, and figure out the best way to transmit it and to up the supply of the kinds of materials like masks that can be used to protect people.
Yeah. Now, look, I think we all can agree, I think, that we know how to end this pandemic. We could end it in a few weeks, right?
In 2 weeks. There's this interesting way of thinking about this problem. If everybody stayed away from everybody else for 2 weeks,
that's it.
Gone.
Right.
The virus is not trying to kill anybody. The virus is trying to survive.
Yep.
And it can only survive if it finds a new host.
Right.
But nobody's going to go along with that. Even for 2 weeks, we're not going to be completely solitary. So what do? If you had a vaccine so everybody was immunized, that's the other way to solve it. We don't have that. If you had a good drug so that nobody got seriously ill, that would help. Then you could get infected and still survive. But But so we're trying to find the right compromise. And this brings us back to the point about asymptomatic people. So if we can identify everybody by testing everybody every day, that itself being somewhat implausible. But if we could do that, and everybody knew within a day of their becoming infected or being infectious, that they were in an infectious state, then we could say, all right, you stay apart from everybody else for a couple of weeks. That's a small portion of the population.
Yeah.
So in our heads, we can figure out how to do this, but putting it into practical terms is
I mean, I have to say, part of me feels like, and of course you're right, this is completely unrealistic, but if people would just fully embrace the fact that in 2 weeks, this could be over. If we just have a certain radical change in behavior. Of course, that's just not how most people think about things.
No, that's what I said in that op-ed you quoted from. That's what I wrote a piece in the Atlantic a few months earlier in which we said.
Yeah, no, I have the Atlantic here. Yeah. So is that an unrealistic hope to ever get the public into the frame of mind where, okay, a new pandemic is spreading across the world. Here's what we need to do, and everybody just isolates for 2 weeks. And
I think that's very difficult, but I do think that it is possible to get people in the frame of mind to understand that if they get tested, anybody who, you've got to prioritize too, is you can't just produce 300 million tests a day and execute them and get the sample to the lab and the results back to people and do the follow-up testing. But if you can say, this cohort of individuals needs to be tested because they're going into a situation where they're at risk. These people need to be tested because they're likely to transmit the virus in a certain circumstance. You test that 5% or 15% that's at the greatest risk of continuing the transmission of the virus, then you can get control of it. Maybe it's not perfect, but all we have to do is get the transmission rate down to an acceptably low level, and then the virus goes away. Maybe it doesn't go away in 2 weeks, maybe it's 6 weeks. But look, it's been 7 months, more than that, actually. But
exactly. Now, I have the Atlantic article, and there is one quote that I wanted to just quickly read that you wrote. You wrote that we believe that expanding current testing capacity remains a matter of extreme urgency, one that justifies a level of intense coordinated work at a national, even international scale that resembles the campaigns we associate with world wars. Very powerful way of describing the need for the kind of testing that you were just mentioning. Now, however, in contrast with that, right, President Trump at times, he's been advocating slowing down testing. And we already discussed how the CDC had been suggesting curtailing the kind of testing that we're doing. And I don't know, did you watch the debate last night? The vice presidential debate a little bit? Yeah. So here you've got Vice President Pence castigating Kamala Harris, saying that she was politicizing vaccines, bringing politics into a domain that really affects people's lives. It's the epitome of hypocrisy. Here you've got these particular political goals influencing the most vital way that we can deal with this pandemic. I mean,
well, I think he was pretending to miss the point about being cautious about a recommendation that comes not from the FDA, not from Tony Fauci, not from the scientific community, but only from, frankly, a disorganized, disoriented leader who has in the past told us that we should be taking drugs that have not been validated, who himself, once he got sick, took every possible therapy, including things that if he weren't particularly ill, he shouldn't be taking, like dexamethasone.
And what do we do? I mean, because the fact of the matter is the various polls have shown that something like only 1 in 5 people would take the vaccine if it were, say, available today.
I haven't seen the number that low, but I've seen under
21%. I saw the number 21% of one poll, so I don't know how accurate it is.
It depends how you ask the question and who you ask. But
yeah, of course, no doubt. But I guess my question is, I don't know a lot about the details that you are intimately familiar with regarding the kinds of protocols that are generally in place to assure that a vaccine is safe. So when I hear the president talking about Operation Warp Speed and rushing things and getting a vaccine before the election, if you were to ask me, would I take that vaccine if it was available today? You know, Kamala Harris had a funny remark. She said, you know, if Trump says it's okay, I won't take it. But if the doctors tell me it's okay, I will. I sort of have a similar frame of mind. But what does the general person do? How do you know, in the context of a country that now is trying to circumvent the usual protocols in order to rush a vaccine, how do you know if it's safe to take?
Yeah, well, I have some residual faith that we're going to be told at least something about how effective any vaccine is in a clinical trial. All the vaccines that are being considered for approval are in phase 3 trials. And I think there are enough people who are concerned about transparency in this process, even if they're not in government and will have access to the data, to reveal what the consequences of taking the vaccine actually are. I do think that side effects are going to be infrequent. I think we're going to have a hard time knowing exactly how infrequent. What I think we will know, but have to understand how to respond to, is how effective it is.
Yeah.
FDA has quite reasonably said that the vaccine has to be at least 50% effective with respect to either blockage of infection or the development of serious illness after you're infected. And I think people have to begin to understand that a decision about a vaccine is not a binary decision. It's not we have a vaccine or we don't. We could have a vaccine that's pretty good, worth approving, worth using, but we have to retain other kinds of precautions to try to reduce transmission, because some vaccines may not be perfect, nevertheless sufficiently useful to use. And I think we have to maintain, if that becomes the case, and it is true that we have vaccines against some diseases, dengue fever, malaria, that have gotten approvals when they're not all that effective, but they're helpful. And once that is the case, people have to understand that we want to encourage people to make better vaccines. We want people who take the vaccine to be, first of all, alert to the possibility of adverse events when you take them. It's hard, just so you're responsive to a change in symptoms. And you've got to be sure those folks understand they still have to take some precautions. They still should be aware they could get infected. And if they're infected, they can transmit the virus. So I think, for the next year, 2, 3, possibly, people are going to have to be adaptable enough to say, these precautions we put in place. And, here in New York City, I would say most people are wearing masks. Most people are distancing. We're behaving pretty well.
Like 90%, I would say. I'd say 10% on the, something like that.
That's right. That depends on where you are, and if you're down with raucous youth in the village, it's different than if you're in the sedate aging Upper West Side.
Yeah, no, certainly that has an impact. Let me ask you. So we learned this disturbing fact from the Bob Woodward book about the Trump administration knowing certain features about the virus and holding it back. That certainly played a role in the debate last night. When it comes to transparency, how do you make a decision about what information to share with the public and what information should somehow be kept under wraps? Do you have a guiding principle for what to do with that kind of sensitive information?
Yeah, I mean, I don't think it's a huge problem, but I do think people have to understand that under conditions like the pandemic, the natural tendency for most scientists who have new information is to try to share it quickly. And one of the delicacies or delicate situations that has arisen here is that scientists, especially under these conditions, are more and more likely to divulge information at a pretty early stage before they actually have what we would call solid data to support a conclusion. And I think all of us have been aware of conclusions that have been proposed, results that have been posted before conventional peer review that have turned out not to be correct. And science is largely a self-correcting enterprise in physics or biology, and mistakes do occur. And here the stakes are high because we're talking about the pandemic and people's health is at stake. And you have to achieve a balance, which I think is very hard to write down as a series of principles between being transparent about early results and convincing people that you're not, that you're divulging information, but you're not yet secure about the conclusions. People have a hard time accepting that. I think science knows things, and when you're a science supporter, you think if a scientist says it and writes it down and puts it into online as part of a preprint server, as you would in archive, for example, and we do in bioarchive, then this is somehow now written in stone, which it's not.
Yeah, no, I find also, people have the view that science is all about one revolution after another, overturning everything that came before. And I try to emphasize to people that science is generally about just expanding the domain that you can talk about with precision. And typically the ideas of the past are not overturned, they're simply extended. So I do think that we have a bit of a mismatch between how science actually works. And I mean, not people who are audience for this discussion typically, but for the general person, it's a pretty different view compared to how science actually does work. But the issue that you raise does bring to mind the question, look, pandemic is obviously something that doesn't care about borders. Science is a field, the beauty of it is that it doesn't care about borders, and we work on something and we look at the preprint server that you just mentioned. The preprints come from all over the world every morning. There's new work coming in. So it's vital that there's international cooperation on trying to combat something of this sort. How has America's response and America's leadership in this pandemic affected our international reputation among the very scientists that we need to work with to really stamp this out?
Yeah, that's an incredibly important question, Brian. I've been mulling a lot about that because one of the reasons people are so perturbed by the terrible performance of our country in this pandemic, that is, we have 4% of the world's population, but over 20% of COVID-19 deaths. How could that possibly happen? And I don't think yet we've eroded our reputation for doing important science. Indeed, most of the things that have allowed us to identify the pathogen, characterize it, develop interesting tests, produce vaccine candidates at unprecedented speed, using not just virus that's been killed or virus that's been attenuated in its potency, but by using viral nucleic acid and viral proteins and having a pretty sophisticated view of how this virus enters cells and grows. Some of that based on antique work or 20-year-old work with coronaviruses, but some of it based on incredibly rapid advances that have been made through the technological tools that only we and a few other places in the world, and in Europe and some places, some in China, I think that's all still viewed as remarkable, and that the botched performance here has a lot to do with American attitudes toward public health, something we might want to talk about in a little bit more detail, and the incredible mishaps that have occurred because of Mr. Trump and his colleagues.
Yeah, it's sort of astounding. I mean, as someone who has had high-level government posts under President Clinton, under President Obama, I mean, we all know that politics always casts some kind of shadow over science. These are not independent realms. But have you ever encountered the kind of influence and the kind of meddling and the kind of manipulation that is going on with this administration?
Absolutely not.
Yeah.
I've watched, I haven't been in a Republican administration, but I've watched, George Bush, and we were very critical of George W. Bush. Not so much his father, but in fact, George W. Bush looks like a scientific messiah by comparison. He ran the PEPFAR program, developed it on his own, and that was one of the great public health efforts in the history of man. And he did have some bizarre policies with respect to stem cell research and a few other things, but he was in general supportive of the kind of research done across the board. And looks like a rational human being, which I think he is.
Right, right. Which now is the low bar for
very low bar to make things better.
Have respect for.
I have a little more respect for the Biden-Harris ticket than that. I think.
Yeah. So
it'll be a big improvement.
So I mean, Trump fed off and feeds off a certain view, at least in America, among a certain fraction of the populace that distrusts expertise, that puts dogma in front of evidence, and approaches the world in a highly non-scientific way. And so I'm often asked the question, what do we do about science literacy or illiteracy in America? And I got to tell you, I've got sort of two views on this, because on the one hand, as you know, this is a World Science Festival event. We run this festival and hundreds of thousands of people come out to the events. Millions of people watch the online programs that we post, which is great. So there is a hunger and an interest in these ideas. So it's not universal that there's no interest in science. And then the flip side, and I know that you've written about this too, and I'll just give my version of it. I know a little bit about genes. I know a little bit about DNA, but I don't know anywhere near what you know. And so you could call me illiterate in certain areas of science, because it's just too deep for any one individual to be a real expert in everything, which is, for instance, when people ask me about climate change, I am reluctant to get into a deep conversation about, I'm not a denier by any means, but I know that a really smart denier could probably wipe the floor with me, because if they've done their work and their research, they may know details that I won't simply be able to respond to. So how do we deal with this puzzle, if you will? Is there a certain body of science that you think every single person should at least know that? Or is it more that we just have to inculcate a sort of scientific mindset that allows people to recognize that there's a rational way of looking at the world and there's an irrational way? I mean, what do we do?
I think this is an incredibly important issue. And I struggle all the time with colleagues of mine who say, we're living in a scientifically illiterate society. Well, scientific literacy is hard to define. And what many of my colleagues who work in molecular biology might think is an illiterate state of mind actually could be pretty literate. So I give a course, as you may know, in the Macaulay Honors College at the City University of New York on science and society, where we try to take up this issue. And my view is that if you can teach people to learn some of the principles that go into how science is done, to learn what the liabilities of scientific exploration are, how science is funded, how science is disseminated, how we get access to information, how it's taught, what forces, economic, ethical, and otherwise, are influencing how scientists make decisions, what scientific truth is, because as you know from thinking about the philosophy of science, it's hard to prove something. And if people can learn these principles of what a rational exploration of the world is all about, and what experimental evidence tells us, and how interpretations change, that there are imperfections, there's fraud, there are all kinds of things that undermine the credibility of science. And if we learn that science is a human activity, that we have to defend ourselves to avoid perpetuating as though any scientific paper is written in stone. Then we taught people about how the scientific profession operates, what its pushes and pulls are, and I think that's the best we can do. And then I would say there are some things we ought to know a little bit about. You were illustrating gravity a moment ago. People ought to have some sense of where that concept came from, what it means, what the major forces are. And I would say likewise that it's really a mark of poor education not to know something about what genes are, how they're encoded, what they do. You don't have to know a lot of individual genes. You have to remember the base pairs, the sequence of base pairs in your DNA. But you ought to know something about the general principles involved. And that's where we have to depend on our educational apparatus, which is somewhat deficient in this country, especially below the university level.
Well, would you be in favor, like, of a surprise question in one of these presidential debates where, Trump or Biden is asked, what is a gene? What is DNA?
I think that'd be great, but that would raise the level of this discourse quite a lot. And of course, the answer might be something about something totally irrelevant. Just as last night, some of the most interesting questions were just totally ignored. People filled up their 2 minutes and more with. I don't understand why a failure to answer the question or to try to answer the question or to say, I'm not going to answer that question, but I'm going to say this because I need to say this.
Right. Yeah. No. That's the debate dynamics. It's its own little universe of
political science. What is that science?
Yeah. Right. Exactly. But speaking of which, so there are many scientists who would not go on the journey that you have in your life. There are some scientists, and I'm around many of them, and I used to think this way myself. We are about discovering truth, right? Transcendent truths that are so beyond these little noisy things about policy and life on planet Earth, and we're not going to spend our time in that domain. So the question is, should we in the educational system have some encouragement that allows scientists to know that it is important to go on the journey that you've gone on, the variations on that theme that others have gone on too? In graduate school, should there be courses like perhaps the one that you're teaching where policy and the politics of science and the politics of funding is part of the training? Because I can assure you that in graduate school in physics, that's like infinitely far away. Right. You're learning quantum field theory, quantum gravity as best you can, electrodynamics, and none of that other stuff matters.
Yeah, well, my view is that, yes, people should have an opportunity to learn about these things if they so choose. Some of my colleagues feel it should be mandatory, and I take a somewhat dim view of that. I think I'm perfectly happy to know that a certain percentage of my colleagues just want to do their science. They don't want to get engaged in politics. I see this frequently, especially in this election year with the pandemic and all the other things revolving around us. When Nobel laureates, for example, are approached about signing a letter that either takes a position on the election or condemns the current administration for something. And I find about 3/4 of maybe 80% of laureates are willing to pitch in and make a statement. This time, when we put together a letter in support of Vice President Biden, over 80 of the new laureates, of the Nobel laureates in America, were willing to sign on to a letter, which is a record, and I think not surprising, because you can't ignore the fact that the survival of the scientific enterprise is closely linked to politics. And at the most primitive level, we know that most science in America is paid for with federal dollars. So that's a requirement to have a Congress that is receptive towards scientific work. And but I think at a time when the findings of science that are essential to the survival of our citizens is being abused, most scientists I know, except for, there are a few who are simply too old to think about what the letter says, or have taken a principled position that they're scientists, they don't know enough about things. And, I draw that line too. I get approached about signing on to some political event in a country I know very little about, and I'm hesitant to sign something of that sort. But I do think that, first of all, we are citizens as well as being scientists. And if we have influence, perhaps we should use it when we care about the issue. And secondly, we can't ignore the fact that society is intimately linked through its politics, through its governance, to the scientific enterprise. And we'd be foolish, I think, to ignore those connections.
Yeah, no, we experienced the same kind of thing. You may recall years ago when we were just starting the World Science Festival, we approached you, Tracy Day and I approached you, would you be an advisor on, and you graciously said yes, which we greatly appreciated. But we had been told that there were going to be very few Nobel laureates that were willing to sign on for much the reason that you're saying, that, science for the public.
And you guys weren't taking a political position. You were simply taking a political position. Science. I mean,
Exactly. It was just the public
I don't understand
about these ideas. But it turned out that not a single Nobel laureate that we approached turned us down. So I felt there was a nice shift toward the recognition of how important it is for the public to know about these ideas.
You may take up controversial topics, Brian, but I wouldn't say
a position.
A science fair is a controversial thing.
Exactly. Precisely right. Did you experience any pushback from your colleagues when you first started to at least spend part of your time outside of the traditional academic world?
I don't think so, because frankly, I think most of my colleagues feel that there's a risk to having people who are no longer doing science or may not have been strong scientifically, helping to run the agencies that give out federal dollars. So, I've never spent too much time in some of the more garden variety things that deal with issues that help microbiologists to survive, for example. So my interest has always been federal agencies and how the government works, how Congress comes to support science, how it provides oversight. And I think most of my colleagues are just concerned about having people who have a reasonable point of view. And I guess I can take it as a mark of commendation that people didn't object to my doing on the grounds I wouldn't be any good at it.
Yeah.
So I've never had much problem with that. But, I have occasionally when we weigh in on things like the recent kerfuffle about the rescinding of a grant to an organization in New York that was
I read about that. Yeah,
how virus is transmitted from bats to humans in China in particular, and that grant was in a sense withdrawn. The money is not money for that grant doesn't go to the investigator at this point, and that's all a consequence of Trump having been asked a question at a press conference. That he didn't know what the grant was, obviously, but he felt he was being told that the grant provided money to the Institute of Virology in Wuhan, and he said, we're going to discontinue that. And then word went down, and that's what happened. So the end of story. Happily, it hasn't recurred, but I don't like calling out my esteemed colleagues and my own favorite agency, the NIH, in public. But I think if we didn't stand up to that and make it and say, this is not acceptable, we don't want this to happen, I think it's important that we speak our mind and recognize that this is not the kind of action we want to see our agency leaders to take. And it has the potential to serve as a very unfortunate precedent, because there are countries in which science is undermined by overt political interference. And we can't allow that to happen.
Yeah. And look, November 3rd obviously is a pretty critical date when we're talking about how this country is going to go forward. If it goes in the Trump direction, it's probably going to be business as usual, which will be catastrophic. But if Biden prevails, and let's just, for argument's sake, because it could well happen, he calls upon you to head up the viral task force to deal with the current pandemic and the next one that no doubt is heading our way. What would be your guiding principles for what we should do to be ready for the next time around?
Sure. Well, let me say, first of all, that I think there's no doubt that, and possibly even in a Trump administration, there would be a commission called by Congress. And the group that I mentioned earlier of former members of Obama's PCAST have actually written a long and thoughtful essay about what the commission, the COVID-19 commission, should take on. And it's clear that there are a number of things to worry about. One is how we organize the underlying science to cope directly with making good tests and new therapeutics and vaccines against the next pandemic. And we do know that there are new ways to do certain kinds of science, especially in the infectious disease domain, that would be even more efficient than what's happened this time. Secondly, we need to be much more conscious of being prepared with the kinds of materials that you stockpile and store up. We need to think about how testing and contact tracing in particular is done. We ought to have a cohort of people who are ready to put in place the contact tracing that is essential for testing to make sense, because testing is obviously not very valuable if we don't follow up with people who've been in contact with infectious individuals. So there's a litany of things that need to be done, and one of which I think is often forgotten but fundamentally important. And I mentioned it very briefly earlier, and that is we need to change public consciousness of what it means to protect the nation's health. It's not just about curing a case of cancer or curing a person who's gotten an infectious disease. We need to pay much more attention in this country in particular to public health, that is, to prevention of disease and to the understanding of what aspects of our behaviors contribute to disease. There are countries that are much less wealthy than we are, and you know what they are: Taiwan and Iceland and South Korea and quite a number of others that have coped much more effectively. Vietnam, another good example, much less effectively with this pandemic, much more effectively than we have with the pandemic, because they have a public health system that doesn't cost all that much and maybe less sexy to prevent a case of disease than it is to cure it. But nevertheless, we just need to change our perspective. The CDC is, under ordinary circumstances, a very valuable organization. It doesn't have the resources ever that it ought to have to protect the country. And we do depend heavily on city and state public health departments. Unfortunately, in this circumstance, we have to depend almost entirely on them. And of course, the quality varies across the country, which accounts for why, as you said before, virus doesn't respect national boundaries or state boundaries or urban boundaries. And we need a coordinated response, and we haven't had that.
Yep.
But I think we can change the public perception of what public health does for not a whole lot of money. Yep. And that should be one of the underlying themes in any commission report.
So we only have a few minutes. There are two other things I wanted to touch
Sure.
on, each of which could fill a full conversation on its own. Apologies for that. But you mentioned cancer. Obviously, that's an arena where you've had a profound impact. Can you summarize, just give us a sort of state of play in your view?
Sure.
I mean, I know that you said that obviously curing cancer versus preventing cancer, perhaps we really should be focusing more on the latter than the former, but where do we stand in that battle?
Yeah, well, let me just say a couple of things about that. First, one of the things that has really impressed me in the last 5 or 10 years is the rapid development of new technologies that can allow us to understand cancer in a much more profound way, using new approaches to look not just at the molecular gyrations in a cancer, but in individual cells. And when you start to do that, you begin to see how much heterogeneity, how much variation there is within a cancer. That mutations are continually occurring, cancers are evolving, and have a kind of plasticity that makes for an evolutionary universe that makes the new therapies that we're very excited about, drugs that specifically target individually mutated genes, new immunotherapies that allow the immune system to attack cancer cells that have foreign-like proteins on their surface. These are remarkable developments, but the ongoing plasticity, the generation of new attributes of cancer cells as cancers grow and metastasize is truly extraordinary. But we now, through what we call single cell biology, have a much better approach to understanding this incredibly difficult problem, because we don't cure as many cancers as I'd like to see us cure. I use prevention as a concept that I think we need to do more with in the human population.
And how effective could that be? And
that's what I'm about to say. So I think we are limited in our approaches to cancer. We know that if nobody smoked, we'd have much less lung cancer. There's no doubt about that. One of the biggest reducers of the incidence of cancer in this country and the reduction of mortality in this country has been through smoking cessation. But that's only one example. Unfortunately, cancer, a disease of the genome in which it's hard to prevent the damage that occurs because some of it is part of the natural process. Cells reproduce themselves many, many times during the course of a lifetime. And every time they do that, they've got to make a perfect rendition of 3 billion pairs of nucleotides and segregate 23 pairs of chromosomes to daughter cells. They don't do that in an accurate manner. And so there's an implicit tendency towards genetic change as normal cells grow. We now know if you take the first 2 cells that develop during embryogenesis, when the fertilized egg divides into 2 cells, those cells already have mutations.
Really?
Yeah, because every time
yes, right.
a mistake are made. Most of those mistakes don't matter because a lot of our DNA has minimal functional penetrance. But
what's the rate? The rate is sort of at the level of, a 0.5%.
No, much less than that. But remember the number, 3 billion base pairs.
Yes, I thought it was on the order of
number.
I got the number wrong. They're right. There's a lot of copying to make there. If a scribe is making copies of the Bible,
we repair systems, but it's not enough.
Yeah.
1 in 10 to the 7th. That's a lot.
Right. Of course.
So now that we have these technologies, allow us to do something really extraordinary. Take 1 cell, let it divide into 2, sequence the DNA in one of those daughter cells, single cell. You can do that, and you can find that the mistakes are occurring all the time. And when those mistakes change the function of an important gene, doing damage. So we're getting a handle on some of those things.
Yeah,
I think that's going to be helpful. I mean, some of that will be helpful with regard to understanding how cancer arises, having a mindset about the plasticity, the variation of cells in a cancer, and the cancers are not they're not monolithic. They're not uniform sets of cells. They have the potential to undergo the kinds of evolutionary changes due to selection that's imposed by giving a drug. So we have all these new drugs. Putting these drugs together is going to be very powerful.
Yeah.
Combinations. So that one thing fails, something else succeeds. It's hard for a cell to escape 2 obstacles to its growth rather than 1.
Yeah, it's sort of amazing and wondrous and frightening at both the same time that the very process that allows for evolution to yield the kind of species on Earth is
we're speciated. You and I wouldn't exist, Brian. If there weren't mistakes and speciation.
Exactly.
But if you want to do that, you've got to tolerate cancer as well.
Exactly. So let me ask one final question. With all of the absolutely spectacular new developments in all of science, but certainly in medical science, medical technology, and so forth that's happening, if you were right now a young medical student just starting out, what direction do you think you would go with the playing field as it currently is?
To me, the biggest scientific problem has to do with energy. If you're thinking about problems that affect the future of mankind, finding ways to store energy, to get more energy out of the sun, for example, relieving our dependence on fossil fuels. These are the things that really, I think, are going to affect the future of human life. If I were confining myself to medical things, like many of my colleagues, I probably would be focused on neuroscience. I actually entered medicine, we talked about that earlier, psychiatry, but like Freud, I took an interest in the structure and function of the brain, but I just found it too difficult. And I think it's still awfully difficult. A lot of progress has been made, especially in the last 20 years. But that's understanding how the brain works, what consciousness is. These are the problems that are at the verge of being approached. Genetics, cancer, infectious disease, these are still fascinating topics, but I do think we have the basic repertoire of principles and technologies. Now it's a matter of working things out. And there are people who differ. I like to start things, and starting genetic exploration of what drives cancer was part of my contribution to science. What's going on now is fun. It's interesting. I work, for example, on forms of lung cancer that are still very difficult to treat. That's an exciting thing, but I don't feel as though we're at a frontier in which we're going over a fence that's too hard to see over. I think we have some sense of what the landscape is like. It's just a matter of working out incredibly important aspects of these phenomena that will allow us to treat, maybe even prevent some of these diseases more effectively. But I think in the neurosciences in particular, they're going to be fundamental discoveries. And let me just conclude on one thing. The other Nobel Prize in my field that occurred this week was the prize for CRISPR.
Yes.
Which is a resonating reaffirmation of the importance of basic science. We now can all envision using the CRISPR editing systems to treat, prevent, cure human disease. But this would never have happened if people had not been obsessively looking at the chromosomes of bacteria and trying to understand how they became resistant to infection by bacterial viruses. And that began in the 1980s. This Nobel Prize went to 2 people out of about 20 or 30 who were prominent in the development of this story. I'm really pleased it went to 2 women. That's great. And I think it's an opportunity for storytellers to say, yes, these people did something that was pivotal in the history of this field, but there was the graduate student who was just looking at organisms that swim around in very salty water and who saw these strange sequences, and people who began to apply the principles of CRISPR to the editing of DNA in human cells that represent the full glory of science, from fundamental stuff to things that are highly applied and are going to be useful in agriculture and archaeology and many other areas of human exploration.
So I said that was the final question, but do you mind me asking one more since it came up? So you mentioned neuroscience, the brain, consciousness as a frontier that at some point we'll be able to explore in some systematic scientific way. What's your gut feeling? Is consciousness something that we will understand by virtue of deeply understanding neural processes? Or as some say, will it forever be beyond the reach of that kind of a mechanistic description?
Yeah, I think we're going to be able to say that consciousness is reflected in can be linked to certain physical attributes, whether it's the configuration of RNA or movement of electrons through some kind of molecular cycle. But I think it's still going to be hard to connect the experience of having a consciousness to those molecular events. And I think it remains to be seen. Let's try to figure out a way to understand what the objective correlates of consciousness are.
Yep.
And then see if we can link it back and make a theory of the whole.
Yeah, no, the hard problem of consciousness, why we have these inner worlds, is certainly well described as a hard problem. And yeah, maybe some of the young folks listening to this will one day contribute to that. So Harold, thank you so much for joining us on this conversation, about science, politics, the pandemic, cancer, consciousness, critical issues. Your insights are incredibly valuable, and thank you for sharing them with us today.
My pleasure, and thanks for your good work with the WSF.
Thank you. Thank you. Okay, talk soon. All right, everybody. So let's do a little more Q&A before we wrap it up today. Again, that was a bit of a departure for the kinds of topics that we usually talk about. Let us know if that's the kind of thing you'd like us to do more of. And again, this one is so vital to the future. Sorry for those of you on the international side of the viewership that it was somewhat America-centric, but what happens in this country has profound ripple effect across the world. So I suspect that many of you, even if you don't live in the United States, are deeply concerned with what's happening in America, which is deeply distressing to many of us. So again, we thank Harold Varmus for sharing some time with us. So heading back to the kinds of things that I can talk to directly, we'll do another 15 minutes or so of questions before we before we wrap it up. Let's see. Aditya asks, what is a naked singularity? And a naked singularity, this is nice because it ties right back to our initial conversation about black holes in the first part of today's session. Black holes, according to the math, have a singularity, but that singularity is encased. It's kind of shrouded within what we call the event horizon. We mentioned this earlier as well. And that shroud, you can almost think of it as clothing that surrounds the singularity. A naked singularity would be a singularity that doesn't have an event horizon surrounding it. It doesn't have any clothing surrounding it. Therefore, we call it naked. And there's a lot of debate about whether, well, as I mentioned earlier, there's a debate about singularities, how best to address them, what they mean, how to deal with them. There have been questions about whether naked singularities are even allowed within the general theory of relativity, and there's been a lot of work done on that. No one's ever actually seen a naked singularity, so it's not as though it's something that we can point to the way we can point to black holes, which now we've actually taken radio telescope images of, but it is a potential quality of the general theory of relativity. Nobel Surfer asks, what do you think about the CCC cosmological model advanced by Sir Roger Penrose? You know, I wish I had something intelligent to say about it. I know Roger has been putting forward that idea for a while, and he has a book on it. I've not read his book. I've not really studied the idea. So unfortunately, I don't feel qualified at the moment to give any real evaluation of that. But at some point, I'll look into it more fully. So if you join us again at a subsequent time, feel free to ask again. Maybe I will have something more useful to say about it. CJ, enjoyed the COVID-19 discussion and excellent witness to the insightful perspectives from Dr. Varmus. Thank you. I appreciate your response to that. Raghav Anand, what is a string made of? That's a good question. Natural one to ask. We know that matter is made of molecules, molecules made of atoms. We know atoms, of course, all of you know, are made of protons and neutrons in the nucleus with quarks and quantum orbits. And you got with electrons and quantum orbits and quarks inside the protons and neutrons. And so with strings, if string theory is correct, which is a big if, the next level of description would be inside those orbiting electrons, you'd find this vibrating filament. Inside those quarks, inside those protons, you'd find these little vibrating filaments. And you'd say, okay, so sequence upon sequence, we find something smaller. When we get inside of a string, is there something that it too is made of? And we don't really know the answer. There are people who have pursued more refined versions of a string, if you will, using things called D0 particles. It's a natural consequence of a formulation of strings, that strings themselves might be, in some sense, a necklace of these little D0. Zero means zero dimensional as opposed to D1, which is one dimensional string. That a string might be sort of a necklace of these D0 particles, these D0 brains. But it could be, on the other hand, that a string, if this idea is correct at all, that's the big if, strings might be it. They might be a truly fundamental entity, and there might not be a notion of something finer within them. It's a kind of unfamiliar idea, because for most everything we encounter in the world, the idea of it being built up from something finer makes a lot of sense. But look, I mean, just by analogy, if I give you a book, the book has pages on which there are paragraphs, and the paragraphs are made of sentences. The sentences are made of words. The words are made of letters. But if I then say, okay, what makes up a letter? I mean, sure, you can talk about the ink on the page, I guess. But if I ask you from a linguistic standpoint, like what makes up a letter, you know, in written language, a letter is a fundamental ingredient. Sure, it has strokes and lines, but they don't hold any linguistic meaning. So the final meaningful ingredient in that linguistic reductionist journey is a letter. and that's it. And, there are many letters in a given alphabet. They're all fundamental. So the fact that there are many of them doesn't necessarily mean that they are not fundamental. So that could be the same thing with strings. Strings may be the end of the line in that progression, in the sense that there's nothing more meaningful to point to when your question is associated with the elementary ingredients of matter. That could be the end of the line. Again, I can't help but stressing that we don't know if string theory is correct. It's a mathematical theory. We don't have the experimental verification, all things that you already know, but I don't want it to somehow go by you that it's a very speculative idea as of today. What else we had? My 10-year-old, according to Kisa, asks, why is space dark? That's actually a very deep question, Dekisa, and your 10-year-old son or daughter, because there was a time when a fellow named Oblers was his name. I forget his first name. Maybe sometime is William Oblers. And he put forward Obler's paradox, which asked, why is space dark? Exact same question. What was Oblers thinking? Oblers was saying, hey, if you look out into space, and if space is kind of uniformly filled with stars, then if you look out into space, your line of sight should hit some star, even if it's far away, and that star gives off light that will travel along that trajectory to your eye. So Oblers was saying in every single direction, your eyeball should encounter an incoming photon, which would mean that the sky would not be dark. The sky would be bright. And this was a puzzle that people began to think about. And the answer speaks to the finite age of the universe. Because if the universe was infinitely old and light could travel infinitely far, because that journey could take as much time as it needs to reach your eye, then yeah, you should encounter photons from every direction in space. But if the universe is a finite age, then in various directions, light simply may not have had enough time to reach your eyeball in the time since the Big Bang. And that would suggest an explanation for why regions of the sky would be dark. So I think the best answer to your child's question, Dekisa, as to why is space dark? Space is dark because the universe isn't infinitely old. And not being infinitely old means that light has not had unlimited time to reach us. And there could be light everywhere out there traveling toward us, but it simply hasn't had enough time to reach us. Very good question. And whatever the name of your 10-year-old is, please tell them to keep on asking questions, as that's what it is all about. What else do we have? Tony Silva, there's no expansion between particles. That's true. And that is a puzzle that some people ask. If the universe is expanding, space is stretching, and you've got two particles, even two particles, I don't know, within this little piece of orange rubber that I'm holding, why aren't the particles in this material moving apart? There's space inside of this. Why is it not moving apart? And the answer is that this is held together by forces that we've discussed. The electromagnetic force, the nuclear force is holding it all together. And because of that force being much stronger, as I demonstrated earlier today, electromagnetic force, remember, stronger than the gravitational force, it can hold things together. It can withstand. But that, I should note, need not always be the case. So the kicker is that if the accelerated expansion of space that we are now witnessing, if that picks up in magnitude, if the acceleration of space accelerates, then it's conceivable that in the far future, the expansion of space will be so powerful that even particles within an object will be pushed apart by the swelling space. Even the electrons in those quantum orbits around the nucleus, the space between the electron and the nucleus may swell, driving the atom itself to rip apart. And so it's not impossible, although we do consider it deeply unlikely, but it's not impossible that in the far future, everything will be ripped apart by the expansion of space. That's what's known as the big rip. One of the other, earlier somebody asked about the heat death of the universe. So in addition to the heat death of the universe could die through the big rip, through everything being ripped apart. All right, a few more questions before we wrap it up for today. Heuretique Sawant asks, if space expanded, where's the whole space? And I understand the question. We normally think of an object expanding into an existing container or realm. Like when bread expands, when it rises into the space within the oven. You know, if I have a piece of material, rubber, and I stretch it, it's stretching within the ambient environment. When we talk about space expanding, it's odd because we want to picture space expanding within an environment too, because our brains are so used to thinking about expansion in that setting, something expanding within something else. Space, we think, may be profoundly different from that picture of ordinary objects in the universe, within space. Space may well be the entirety of reality. No container, no external. Space is the be all and end all, the whole shebang. When space expands, what's happening is the fabric of space is stretching and thereby creating new space that the universe then inhabits. It's not as though the space is expanding and encroaching upon pre-existing territory that the universe somehow hadn't earlier acquired. No, space may be stretching and creating the new space, and in that manner, not filling more of a pre-existing domain, rather creating a larger domain than previously existed. That's the difference. All right. So Jacob says, but Professor Greene. I'm not sure what to do with but Professor Greene. I guess I could take that question anywhere. But Jacob, if there's another half to your question, feel free to include it somewhere else. Spin foams. Do the people in the chat know about J.J. Sakurai? Spin foams, I don't know. J.J. Sakurai, of course, a vital force in the development of physics. Quantum mechanics has a great textbook on quantum mechanics. I don't know. I'm not exactly sure why you're asking, but I don't know. Maybe. Saad Raza, if the universe is 13 billion years old, then how can we see 92 billion light years away? Yeah, that's a sounds puzzling at first. If the universe is 13 billion years old, right, then you'd think that from any given direction, at most you could see is 13 billion light years in every direction, because as I said before, you can only see in directions where light has had enough time to reach you, right? I shouldn't say see in directions. You only see at distances from which, that's a better way of saying it. You can only see distances from which light has had enough time to reach you. Farther away, they wouldn't. So what do we mean? And I often say this too, when we don't actually say that the universe's radius is 92 billion light years. We don't say that its radius. We say rather its diameter is 92 billion light years. We say that its radius is about 46 billion light years. So we could see 46 billion light years in each and every direction. Why is that? Well, it has to do with what we spoke about earlier. The universe is expanding. So if the universe was static, right, it was just this big thing that was out there, then you're right. The farthest that I could see would be 13 billion light years, because that's how far light could travel in 13 billion years, period, end of story. But in a dynamic universe, an expanding universe, light can be emitted from one location, and the source of that light moves away from us. So when I see that light, the actual object that emitted that light is now further away because it moved away. It could be 45 billion light years away. So I'm seeing it from the moment when it emitted the light, but its location when I then receive that signal is much larger than 13 billion light years, because it has been moving away while the light has been traveling to my eyeball. That's the basic idea. All right, Woody, final question I'm going to do. Woody asks, I think Woody had a question before. It's a double question. Oh, sorry for everybody else who didn't get any in. How do you think the universe will end? How do I think the universe will end? Well, I think it's quite likely that the heat death that we already spoke about will be a key moment in the far future of the universe. I do believe, as far as I can tell based on my understanding of physics, that ultimately planets will either spiral into their star, we discussed that earlier, from gravitational radiation, or they will wander off into space, and then stars will supernova, some will turn to black holes. Ultimately, all of these clumpy objects will disintegrate. I think it's likely that protons have a long but non-zero lifetime before they fall apart into more fundamental constituents like pions, neutrinos, electrons, and things of that sort. And so ultimately, all structure will dissipate into particles that will spread wider and wider. And it's likely that that will happen on the order of 10 to the 100 years. So it's a long time. You don't have to worry about it. But in a fundamental sense, that is a vital step. Now, is that the end of the universe? Not necessarily. There are weird things that can happen after that, because when you have a lot of time and you've got a lot of particles wafting around, and we may have a source of energy coming from the accelerated expansion of space, yielding a cosmological event horizon, analogous to a black hole event horizon way out in space. That cosmological event horizon, according to Stephen Hawking and Gary Gibbons, gives off heat in the form of particles, in the form of radiation. So we may have a source of radiation within this large cosmos, allowing particles to interact. Ordinarily, most of the time when the particles interact, not much will happen. One will bounce off another, they'll pass by each other, but on occasion, on rare occasion, a couple particles may stick together. And on rare occasions still, clumps of particles may stick together. And on rarer occasions still, those particles may clump together to yield interesting structures. We've spoken about the possibility in other of our gatherings. Even a human brain may, on rare occasions, spontaneously form in the void, so-called Boltzmann brain. But putting all those crazy ideas to the side, it's also possible that on rare occasion, the conditions necessary to ignite a new Big Bang may happen. So it's not impossible that the universe may go through cycles where the Big Bang that gave rise to our realm, maybe the conditions necessary for that, rare as they may be, may happen again. And so things may start over. We don't know for a fact, one way or another, what will happen. Sensitive to this question is whether this accelerated expansion will continue forever and thereby have this endless source of radiation and particles. But that's certainly a possibility for what may happen in the very, very far future. All right, it's about 2:20. I think I'm going to wrap it up for today, guys. I enjoyed this discussion with you all, your questions. I enjoyed my conversation with Harold Varmus. Again, my thanks to him for joining us. If you guys have suggestions for people that you would like to have me in conversation with, please send them to us. You can put them in the chat. You can send them to the World Science Festival. You can find our contact information right on the website, or put it just in the YouTube chat if you remember to do that later on, or tweet it at us. But we have a number of people lined up going forward, and I look forward to those conversations and continue to address your questions going forward. So keep an eye out for our next session. It may be next week or the week after. We're going to try to do every week, every other week, or so forth, but we'll keep these going. And I enjoy your continued engagement with these ideas. So until we meet again, take care. See you then.